So today we are going to start into the other half of Unit 10, which deals with sound. Hooray! I think there's some note sheets. Yes, there are. Sure. I punched this on the wrong side, but you have to back. So today we're going to start talking about sound and all of its glorious effects. Sound is a mechanical longitudinal wave. This means if it's mechanical, it has to have a medium to wave in. Very good. And since it's longitudinal, that means it has compressions and rarefactions instead of crests and troughs. So we have compressions and you can't say it? No, rarefactions.
Rarefaction!
Rarefactions. I told you about that kid that saw me at ACB. Oh yeah. There was some kid I hadn't seen in 10 years that came up behind me at ACB.
Rarefaction!
And we laughed, and everybody around us thought we were insane. Which is probably true. So we learned some vocabulary last time that went with waves in general. We learned about mediums, we learned about compressions and rarefactions, we learned about longitudinal. We also learned about frequency, and frequency was how fast I got to wiggle the wave. And so the pitch, how high or how low the sound seems, is determined by the frequency of the wave. So the pitch goes with frequency, frequency goes with pitch. Generally speaking, a guy talks with a
Low frequency.
and girls speak with a
High frequency.
and of course that's not true all the time with all people, but as a general rule, it applies.
He knew where it was going.
I don't have a graph writer in this room, I just have this cheap thing. So, we'll let you guys just play your favorite songs later.
Weird Al. I'll play Weird
Aren't I good?
So majestic.
Up here, these are high frequencies, which means they're wiggling very fast, and down here are low frequencies. So those are going very slow. So we have high and low frequency. That's not the same. People get confused when I say high and low, and some people think when I say high, I mean loud, and low, I mean soft. But no, high is like this, and low is like that. Not loud and soft. Loud and soft goes along with amplitude. So the amplitude of the wave determines its volume. And of course, we remember that amplitude measured how much? It was how far from the rest position, but what did I have to do to make it have a bigger amplitude? Use more force. I had to put in more energy. So the amplitude is a measure of how much energy it is, so that should make sense that it's volume with sound, because if I put in a little bit of sound energy, it's very quiet. Wow, Mars, you don't trust me? So if I put in a lot of sound energy, it gets loud! Mars is already covering his ears because he's seeing that one coming. She's smart here. Of course, the speed of the sound is determined by the medium that it's traveling in. We learned that within a given medium, we're going to travel at a constant speed. But if I change that medium, or I change the way the medium behaves, then it will change the speed of that. And of course, that works in sound also. But what is a little odd about sound is sound travels fastest in a solid and slowest in a gas. This is different than you. You run through a gas pretty well, you go into a liquid, you're going to slow down. You try and go through a solid, you're going to stop. But sound actually goes the other way. Sound goes slowest in a gas, and it goes faster in a solid, and faster in a liquid, and even faster in a solid. And so at room temperature in an air, sound travels at 343. You are expected to know that number. So please get to know that number, 343 meters per second. So that is how fast sound travels through your typical air that's inside. Outside, of course, it will change with temperature. Now, why does sound travel faster in a solid than it does in a gas? Does that make any sense at all? It does if you think about what kind of wave it is. It's a wave that has compressions and rarefactions. So we're scrunching stuff together and stretching it apart. Now, in air, we have lots of spaces in between our molecules, and so there's lots of scrunching room. And so you have to move a lot farther before you can compress it and expand it. Whereas if you're in a solid, how far do you have to compress it before you smack into the guy next to you? Hardly any. And so any little compression, you move very, very quickly through that because all the molecules are already touching in that nice position. So sound actually, since it's that compressional wave, it travels much faster through things that the molecules are already closer together. On the other hand, if we're talking about in air, there is a formula for what is the speed of sound in air at any given temperature. And the formula here is 331 plus 0.6 T, where T is our temperature in centigrade. So if we are freezing outside, what would the temperature be if it's freezing? 0. So if it's 0 times 0.6, that would be 0 plus 331 would be? Hey, 331. So if it's freezing outside, the speed of sound is only 331. Here in this room, it's about 343. So it gets slower when it gets colder, because if it's colder, then the molecules in the air are moving slower, so it's going to take longer for that to pass along. And so if you're trying to break the sound barrier, would you want to break the sound barrier on a hot day or on a cold day? On a cold day. On a hot day, you got to go faster to break that sound barrier. On a cold day, then it's slower. Yeah, so when they first tried to break the sound barrier, they always tried to do it on a cold day. It was easier to do. Okay, so we learned about a wave formula. And the wave formula that we learned was V equals F lambda. Do you remember that one? So here we get to use that. V equals F lambda. We're looking for what?
How large?
Is that the V, the F, or the lambda? That's the lambda. So if I want to look for the lambda, that stays there, and the F needs to move underneath the V. So it's going to be lambda equals V over F. And of course, the speed of sound in air is 343. And we said it's 150 hertz sound, so that's 150. So 343 divided by 150 is 2.3 meters long. I am a little less than 2 meters long. So this sound would be bigger than me. Now you're saying 150 hertz, is that real low? Well, that's a fairly low sound. But you guys have all heard boom boom cars, right? The cars that go by and go boom, 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 boom. That's all you ever hear out of them. Okay, the boom boom cars, the boom that you hear in most boom boom cars is around 50 hertz. So if that's 50 hertz, if that's 3 times smaller, then this wavelength would get 3 times bigger. So that would be around 6 meters long, which is about the size of this room. Have you ever noticed that boom boom cars are really hard to figure out where they're coming from originally? Yeah. All you hear is this boom, 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 and you're looking around, and then you finally see one that's shaking, and you know it's that one. But it's hard to figure out where that sound is coming from. We find that it's very hard to find the direction of a noise if the sound wave is bigger than you are. And so in all these, it's going to be hard. So the low frequency waves are hard to figure out what direction they're coming from. But the high frequency wave, if you have a little bird chirping, you're like, oh, it's rare. And you know exactly where it is because that's that high frequency. It's easier for our brains to pick up on. So that's there. Acoustics is what we're going to be studying this week. And acoustics is the study of sound. We're going to figure out how to amplify it, how to cancel it, how to design buildings to minimize noise, all that kind of stuff. I went to a concert at the TAMU Fine Arts Center. Has anybody ever been to the TAMU Fine Arts Center or the LCC one? They're both very good. They're well planned out little things, and they got funny things on the ceilings, and the whole room is shaped strangely. And the whole design of the building is designed so that if you're on stage, you can be talking in a voice like I'm talking, and everybody can hear you, which is pretty cool. Whereas the noise from the seats doesn't transfer to the stage nearly as well as the sound from the stage comes out to the seats, which is good because otherwise they can get really distracted up there with all of you guys making noise in the audience. So that's what acoustical design is we try and design a building so that it's either trying to emphasize the stuff or it's trying to minimize the noise. Another example of acoustical design that you guys are very familiar with is at the movies. How many people have been to the movies? I've been to a bunch of different theaters in my life, and every one of them has something that's the same. The theater is basically a big cement cavern, and it would echo like crazy, except what is on the walls of every theater I've ever been to? Some sort of material. You got some sort of fabric that's on the wall. Now, do they just stick it flat on the wall, or do they make it bumpy? Yeah, it's bumpy. It's like every foot it sticks out a little bit, and so you've got this texture that's to this. And the whole point is you want the sound to come from the speakers and go into your ears, but you don't want the sound to be bouncing off the walls and coming into the ears. So they put lots of stuff that will absorb sound up on the walls so that I'm stuck in this cement cavern. I don't want it to be echoey. It's echoey in this room. I can actually hear myself echo off the wall and off the back wall and hear myself talk. It's really weird. So I don't like it. We need to put fabric on the walls in here. But I don't think they'll let me do that. Yeah, that can be real distracting if you're like, have you ever seen somebody freak out when they have to sing the national anthem and they're doing it over the microphone and then they hear themselves echoing back later and it's all, yeah.
I've done something like that before while I'm singing, but I've heard myself on the microphone like a few seconds after I was talking. It just slowly devolves into me laughing.
Yeah. It is, it's just kind of a strange sound to hear yourself delayed like that. Doppler was an acoustical scientist. Has anybody ever heard of Doppler before?
Yeah.
Good. Doppler was a scientist who studied acoustics, and he noticed that sounds sound different if you're moving. What happened was he lived way back about 150 years ago, and back then people used to travel from town to town. They used to travel from town to town on these things called trains. Yes. So you'd get on the back of a train and you'd ride out, and if you were a politician, you would come to town, and you would be in the back of the train, and then the train would pull into the station, and you would talk standing there on the train, and everybody else would be on the station, and you'd just give your little speech, and then it would go away. And to welcome these dignitaries, they would have bands that would perform, and so the town would have a band, and they would play when people were coming in. Well, one time Doppler was on a train, and the band was playing, and he noticed that the band sounded different when he was pulling into the station than it did once it stopped. And he thought, well, this is really weird. Let's do some experimenting on this. And so he decided that he was going to do an experiment. So he hired one of the trumpet players, and he said, what I'm going to do is I'm going to go riding by on the train, and when you see me coming by, I want you to blast one note and just keep that one note solid as I go past on the train. And so when he did that, he noticed that the frequency he heard dropped as he went past it. He thought, okay, that's interesting. Now that I'm moving, well, what would happen if he was moving and I was stationed there. So he stood on the platform and he had the trumpet player be on the train going past. And when he tested it both ways, he found the same thing happen. It didn't matter whether the sound source was moving or whether the listener was moving. What happened was you heard a different frequency. And what happens is you basically, as something is moving toward you, you hear a frequency that's actually higher than what's really being produced. When something's moving away from you, you hear a frequency that's lower than what's being produced. So what happens is when it goes past you, it goes from the too high to the too low, and you hear this distinct drop. You hear this all the time when you're flipping channels. If you're ever bored on a Sunday afternoon and you're flipping through channels, there's this thing that shows up on Sunday afternoons called NASCAR. I don't know if anybody ever actually watches this thing, but if you've ever been flipping through channels and you know it, as the cars go driving past the microphone, what do they sound like? Yeah, they all go, near, near, near. Do you ever go, right? Never. It always goes, near, near, near. Because you're hearing it too high and then you're hearing it too low. You hear that drop in frequency as they go by you. You never hear it go up. That's really very strange. We used to hear it really good on the interstate back before they did the little flyover on Mines Road, where Mines Road hits the interstate. The train used to have to blow its whistle right there, but it doesn't have to now because they don't hit anybody anymore. Yeah, it used to happen on a regular basis. But it was fun because, especially if you were going south on the interstate when the train was going north, when it hit Mines Road, and they would blow their whistle and you would hear it'd be, you'd go past it. My kids would go, hey, Doppler effect. They were only 6 and they knew what that meant because they had me for a dad. So they knew Doppler. Excuse me. So Doppler figured out that things are higher or lower. Now, why does this effect happen? Well, imagine that I have a whole bunch of balls in my hand, and I'm throwing them to bounce them off your head. Okay? So I'm going to throw a bunch of balls at Pauline's head. So if I throw the balls 1 per second, and I'm just standing here, how fast are they going to hit her on the head?
Not the same.
About the same. If I'm throwing just this constant nice speed at her head, if I'm letting go at 1 per second, then they're hitting her head about 1 per second. But if I'm walking toward her and I'm still throwing at 1 per second as I'm getting closer and closer and closer, the distance the ball needs to cover gets smaller and smaller and smaller, and so it's actually going to hit her faster. You know, the one that I throw from back here has to cover a bigger distance, but as I'm getting closer, each one gets to cover a shorter and shorter distance, and so bang, 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 they start hitting her faster than I'm throwing them. On the other hand, if I'm backing up and I'm throwing them, now the distance is getting bigger and bigger and bigger, so I keep throwing them at 1 per second, but they're hitting her with a slightly larger interval than 1 per second. So the frequency she feels them is different than the frequency I'm throwing. Does that make sense? So that's essentially what's happening at the Doppler effect. So if I'm moving toward each other, the sound is a higher pitch, and if I'm moving away, the frequency is going to drop. We call the increase in frequency a blue shift, because light appears to affect this way also, and you're shifting toward the blue end of the spectrum, which is the higher energy, the higher frequency. And a red shift is a drop in frequency. So you should know 2 things. Blue shift, increase in frequency caused by something moving toward you. A red shift is a drop in frequency caused by something moving away. So those are key words to go with Doppler. And of course, when the nice officer pulls you over and says, you were going 47 in a 20, how does he know you were going 47? He bounces radar off of you. And if I stick a known frequency toward you and it bounces off at a different frequency, then he reads that new frequency and he quickly plugs into this formula. Okay, does the cop actually pull out a calculator, plug into this formula? know it's built into his little radar gun and it just says a number. But the radar gun was programmed by somebody who actually knew physics, and they're actually plugging in this stuff. So FL stands for the frequency heard by the listener. FS is the frequency emitted by the source. The V's are just the speed of whatever you're using. Most of the time that's sound, so that would be 343. VL is the velocity of the listener, and VS is the velocity of the sound source. So if both the listener and the source are both moving, you need to plug in both of these. But most of the time, one of you is moving and not the other. So you have to figure out which one that is. So if the car's horn emits a 1490 hertz tone when stationary, what tone is heard when the car is coming toward you at 27 meters per second? So we're going to use this nice, fantastic formula. And we're going to say, okay, the car's horn emits this tone, so this is my source frequency. So that would be the first one, so that's going to equal 1490. And then we're going to have V, and the V, of course, is going to be 343. And that 343 is going to be top and bottom. Now we have a plus or minus the listener, a plus or minus the source. Now, we're looking for what tone is heard when the car is coming toward you. Is the car the source or the listener? It's the source. So we're looking at the car speed needs to go here on the bottom. So the car is coming toward me at 27. Does it say anything about you moving? So since I'm not moving, then this is plus or minus 0. So obviously this has no effect on our math. And now I have to figure out the plus or minus down here. Well, it's going to make a difference whether it's a plus or a minus. Now, you can spend lots of time figuring out, well, I have to memorize whether it's plus or if it's minus using these rules that are already written here, or you can just think. And I know some of you would prefer to just memorize your way out of life, but I would prefer that you think. And it makes sense here. If the car is coming toward you, do we expect it to be higher or lower? We expect it to be higher, okay? So if I know this number has to be bigger than 1490, then I have to say, okay, do I want to make my denominator bigger or smaller to get a bigger number? Smaller. And I want to make it smaller, so it makes sense that, hey, that would make more sense if that was a minus rather than a plus. If I have a smaller denominator, I'll get a bigger number over here. So this would probably be a good time to draw a calculator if you haven't done that. So what'd you get? I got 16, 17. After rounding, I want that to be 16, 20 hertz. So it got higher. If it goes past me, what would be the new sound I hear? What would be the only thing that changes? Yeah, the minus turns into a plus. So if you just highlight the formula up above, change that minus to a plus. Suddenly I'm down to 1380 hertz. So when it went past you, you would hear that drop from the 1620 down to the 1380. That's why you hear the near as it goes past. This is easy, right? Of course it is. Everything in physics is easy. We love it. here we have a beautiful video of a sound. So the fact that the video quality stinks doesn't matter because it's all about the sound here. So this was somebody videotaping an ambulance going by, or a fire truck. I think it was a fire truck. And this is in England, so they have different sirens over there. So yeah. So, when did you hear the shift? Once it passed. And obviously there's not some guy in the ambulance going, okay, I'm going to go past and flip, and he flips the switch, and it goes to a different thing there. You hear a distinctly different drop in frequency there. So, it's kind of fun that way. But that's a good example of Doppler. All right. When your parents yell, turn down that noise, and you say, but it's music, man. Who's right? You can't know until you know the definition for music and noise. So music is made of frequencies that are planned and sound good together, while noise is random and does not sound pleasant. Let's pretend everybody in here can actually sing. I know that's not true because I've heard you sing Happy Birthday. Anyway, we'll get to this. We're going to pretend that each of us are gifted at singing. And so if we are all talented at singing, and we all choose our own favorite song, and we all beautifully sing our own favorite song all at the same time, then individually we are making music, but collectively we would be making noise. Definitely making noise. So no matter how pretty the individual components are, if it wasn't designed to sound good together, have you ever heard like when orchestras are tuning up before they start?
Yes.
Yeah, that's noise. Each individual instrument is making a nice sound, but it's not planned together and it just sounds.
Have you heard when orchestra members switch instruments? It's also kind of like that.
I would imagine.
Like when the flute players switch with cello, and like they just switch around their instruments.
Yeah, I don't think the talent instantly switches over to the new instruments. So, yes. So, who is right between you and your parents? Yeah, when your parents are screaming, turn down that noise, they're emphasizing the part where it doesn't sound good to them right now. I just came home from work and I'm cranky and I need some alone time, man, and you've got that music blaring, and I say, turn down that noise! And you say, but it's supposed to sound that bad. So technically, you are correct, because it was designed to sound that bad. And some of you have music that really is sounding that bad. Anyway, we have another word here. These are called consonances. Frequencies that go together are called consonances. And it turns out that there's math behind it. The notes that sound nice together make small whole number ratios. I know there's a little section that's missing. We'll get to it, trust me. Just skip that one little paragraph and jump down. But frequencies that sound good together, like that's a major chord. That's a minor chord. The emo kids like that. Now, you go anywhere in the world and you play these two notes together, and people are going to say, that doesn't sound good. But you go anywhere in the world and you play these two, and they're going to say, yeah, I like that one. There's a reason for that. And the math is, again, we've got like a 3 to 5 to 7 ratio in this chord. And so the ratio sounds really good. That's a really high number ratio. It's like 11 to 17 or 235 to 392 or something weird like that. So we end up with these things that don't sound good. So the ones that do sound good are called consonances. The ones that do not sound good are called dissonances. Now, a lot of people confuse music and noise with consonance and dissonance. That is not the case. Noise is not dissonant and music is consonant. Consonance and dissonance are both musical terms. And so you use this in there. We create tension musically with dissonance and then we relieve it with consonance. So if you've ever heard the majestic piece, okay, anyway, okay. You can tell my skills don't lie in piano anymore. When you play realistically, is that pretty? No, that's dissonance. It's intentionally put in there so that, yeah. So when you go to the second note, suddenly, hey, that's nice. It sounds good. That's the tension. That's the relief. If I can play, that actually works. So dissonance and consonance are both actual musical terms. Now, who was the guy that first figured out that there is math behind what sounds good and what doesn't sound good? Yeah, a lot of people think, oh yeah, it must have been Beethoven or Mozart or somebody like
Those are
that.
like the only two people I know.
But the first guy that we know about that figured out that there's actual math behind it was some ancient Greek guy who was a major math nerd. Pythagoras. The same guy that came up with the triangle ideas. Yes.
Everyone knows.
So Pythagoras was also the first one that noticed that there's a mathematical relationship between the notes that sound good together and the ones that don't. So this whole idea of consonance and dissonance having a math behind it has been around for several thousand years thanks to Pythagoras. So kind of interesting. Certain things hang out forever. Now, octaves. If you're into music, obviously you know what an octave is, but if you're not into music, then it's a little bit harder. An octave is a note that sounds the same, but it's not the same note. So if you think about a girl and a guy both singing the same song, but he's singing lower than she is, but they're actually singing the same notes, she's singing an octave higher than he is. So if we're just playing notes, these are clearly not the same note, not the same note, not the same note. Hey, these sound similar. Now, clearly that one's lower, this one's higher, but that's the same note. And so when we hear the same note, what we're hearing is this higher one is exactly 2 times the frequency of the lower one. That way, if you think about crests and troughs, when the slow one is cresting, a high one is also cresting. It just crested once in the middle too, and then it crests again when the next one does. And so it's hitting very similarly to your ear. It's just going exactly twice that. And so your body likes that idea. And so it says, yeah, that's just going to be a nice octave apart. So octave is doubling the frequency. So there's going to be really tough math here. If we have 256 hertz as middle C, this note, if I jump down an octave, what's that? Yeah, I have to divide by 2. So that'd be 128. So if I go down another octave, that would be 64. Those of you who are good at your computer stuff, these are real fundamental numbers. So if that's 256 and I go up 1 octave, that would be 512. If I go up another octave, that would be 1024. Another one would be 2048. So it's really tough math there. I multiply by 2 or I divide by 2. Ooh.
I can't do the do.
I know, it's very tough. Okay, so jumping up to that one little paragraph that we skipped somewhere in the middle there. For those of you who didn't pay attention, you've been writing in all the wrong answers in the wrong spots here. But now we're going to get to fluctuations in volume. Beats are fluctuations in volume due to interference between 2 similar frequencies. What does that mean in English? What is a fluctuation? Some of you have wildly fluctuating grades. I I got a 93, then I got a 62, and then I got an 87, and then I got a 49, and that would be fluctuating grades. Others of you have grades that are 88, 88, 88, 88. I'm never going to get Smarties. And they're not fluctuating. So, yeah, a fluctuation is something that varies quite a bit. So we vary in volume. Why do we vary in volume? Because of interference. Well, there's two types of interference, right? So if we have constructive interference, then the sound is going to get louder, and if we have destructive interference, the sound is going to get softer, and so we have it fluctuating in volume because it keeps changing whether they're working together or fighting each other. The best example I have of a mental picture of beats is being on the swings. How many of you have been on swings before? Good. If you've ever been on the swings next to somebody, then you know about beats. Because you're on the swings next to somebody, and you start off and you're like, hey, look, we're swinging right together, but it doesn't last for very long. And then you're like, hey, look, we're exactly opposite. And then before long, you're like, hey, look, we're swinging together again. And before long, you're, hey, look, we're opposite again. And you see this happen over and over and over. What's happening is if you're swinging together, of course, you know that you can really rock the swing set that way. We used to tip our swing set over and get going real good like that. Never mind. So that would be the constructive interference, and when you're exactly opposite, then that would be the destructive interference. You see the same thing with blinkers. If you've ever been in the left turn lane and you got like 6 cars ahead of you, sometimes you'll see the same effect happening with the blinkers, where they're blinking together, and then they're completely off, and then they're together again, and you see the same thing. So it always happens when things are similar, but off a little bit. So we are now going to get some beats. Before we get our beats, of course, our homework is going to be
piano beats.
Yay! But to get to our beats, here I have a tuning fork, and this tuning fork is on top of an acoustical chamber. This box is designed to make the sound that the tuning fork makes bigger. It amplifies that sound, so that's an acoustical design. And so this is vibrating at a nice known frequency, and this amplifies the sound. So this vibrates at about 260 hertz. That's the frequency of this tuning fork, at least it was when it was first built, but it's suffered abuse over the last 3 decades.
Someone hitting it.
Yeah. Well, it depends on what's hitting it. This doesn't hurt it too bad, but some other things I'm sure have abused it over the years. Now, what I have here are some nice, interesting sounds. And so what I can do is I can make the computer generate frequencies. And the computer generated frequencies are going to mess with these frequencies. So here I'm going to play for you 255 hertz. Well, I said this was 260. So how far apart are these? 5 hertz. So what you're going to hear is 5 beats per second. The number of beats you hear is going to be equal to how far off they are in frequency. You can't tell if I'm too high or too low, you just tell how far off you are. And so you will only hear these when both are playing at the same time. So I'm going to get this started, and I'll get this started, and I'll stop this, and you'll stop hearing the beats, and then I'll start this again, and then you'll hear the beats again, and then this will shut off, and you'll stop. Okay, anyway. That's about right. Ready? So could you hear him?
Yes.
Now, did you hear about 5 per second?
I don't know.
Yeah. Okay. So, now, what if I switch to 263? I was at 255, and 255 to 260 was 5 off, so we heard woo 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 5.
It's a stooge.
Now I'm going to be 263 to 260, so now I'm only off by 3, so it should be more of a woo woo woo, right?
Seriously, it's like 3 stooges here.
And again, you notice that you only hear them when both are playing at the same time, right? Because it's the two sounds messing with each other. If I switch to 259, this should be off by about 1 per second.
Mr. Paulson,
Yes, ma'am.
they're here to pick up around Salazar. Can you please send them to the front office?
You betcha.
So
Thank you.
I know your work.
Good enough.
Get it?
Again?
Why are you
doing it?
All right. Hope you've been brushing. Okay, so this one is about 260. So what should we hear? We should hear none if this is perfect at 260. But this isn't perfect at 260, so I want you to try and figure out, you're going to hear a very slow cycle. Try to figure out about how long it takes to go through one. Could you hear it? You kind of hear it go big, and then it was starting to go down, and then it was just starting to come back up again. It's probably like off by an 8 hertz or something like that. So it takes like 8 seconds to go through its thing.